Hey everyone and welcome to PrepFusion. So this is the lecture 18, basically continued version, because in the previous lecture I had to stop right in between the questions. So in this lecture we'll solve very new questions, okay? And like this will be different, so try it out by yourself, pause the video, try it out by yourself, then see the solution, okay? And after this, like after the questions, then I will give you a brief overview of the whole chapter on what you did, okay? I will revise the whole chapter, just a brief overview in 10 minutes, like what you did and how to make the connections and how to solve, right? The whole throughout, what things are important and what things are not that important, okay? What things if you don't understand, it's fine, okay? But the things that you have to keep in mind, those things, right? Yeah, those things I will do after the end of the questions. So first, this is the question. So this question is, write the state space representation for the given block diagram. So I haven't given a simple y and u, okay? That means like directly I haven't given y as a like equals to some transfer function into u, right? Now this y is a matrix. Y is a matrix because first thing to notice is here, right? I have two outputs, right? Two outputs, and I have two inputs. That's why what will be my order of the transfer function? Like I have taught you, right, in I think first or second lecture, that if I have two inputs and two outputs, what will be my order of the transfer function? It won't be just a single transfer function, right? There will be four transfer functions, okay? There will be four transfer functions, basically t11, t12, t21 and t22, okay? I have already taught you, like in the first or second lecture, I don't remember, okay? Whatever lecture I have taught you, right? So we'll solve that also, we'll write that also, then you will understand what I am talking about, okay? So we have to find the state space representation. So like we haven't given the block diagram, I haven't shown to you, like we haven't given the block diagram. Here what we see, we have two inputs and two outputs. Whenever multiple number of inputs are given, right, then just be a little bit careful, okay? Just be a little bit careful, because chances of mistakes happening are very high, okay? Because you have to find the forward path gain from this one and then from this one. So just be careful and solve it a bit slowly, okay? Don't hurry, okay? Don't hurry. So we have to find the state space representation. So what do we do for state space representation? We first write the state variables, then we remove the integrators, right? And after that we check the like x1 dot and x2 dot, whatever path there is from each state variable and the input, okay? So yeah, let's solve, then we'll understand. So we have done this type of question multiple times, but this is a bit different because we have two inputs and two outputs. That's why this is a bit different. So let me copy this, okay? And let me paste this over here, okay? And what I will do is name the state variables, basically. So on the top I am writing x1 because here I have been given y1. It's just a convention thing, okay? Whatever convention you choose, like then it will be transpose, right? Rows will be columns and columns will become rows, that they will interchange. So what will be this? Let's assume this one as x1 and this one as x1 dot, and let's assume this one as x2 and this one as x2 dot, okay? So assume the state variables. Now what I will do, I will remove the integrators. So if I remove the integrators, right, if I remove the integrators, what happens? Now I will write this x1 dot for u1, x1 and x2 and u2. I have multiple things, right? So just be a little careful. So what is my x1 dot due to u1? So one thing I have to notice, is there any loop forming here? So can I see any loop? No, I can go like this one. No, this loop is also not possible. This is a loop. No, this is also not a loop. Okay, there isn't any loop here, okay? So just be careful. If there is a loop, then you have to write it individually, right? Right, in SFG chapter I have done it. Write it slowly for each state variable, right? Write it very slowly, okay? For each of them. So for x1 I will write there, I will write like this one, x1 should be equals to x1 by x1 should be equals to the forward path gain times the associated loop gain divided by the determinant, right? So I will write slowly, but here as we don't have any loops, right, so I can write directly here. I can write directly. So I can write that this x1 has only one forward path, that is this -1. Does it have any other forward path? No, it doesn't, right? So it will be minus x1. Now this x2, right, does this x2 has any forward path? From here Okay, from here I can go, okay, from here I can go to the x1 dot. Okay, so there is one forward path of +1 x2, and determinant is 1 because there are no loops, and associated loop gain is also 1 because there are no loops. Okay, but is this the only path? Is this the only path? I just gave you a hint just 10 seconds ago. This is also, like, this is hidden, but this is also a path, right? This is also a path. But what is the difference here? The difference is this one. We have -1 multiplied. So this will be -1 into x2. Okay, so you have to just be careful about the different forward paths. Okay, so yeah, this is -1 into x2. Okay, and like what thing you have to notice is, like, I could have written it in one line also, like in one line. So this will be like, if I would have written SFG formula. So what does this mean? So this is by 1. What does this mean? This means forward gain, okay, times 1, because the loop gain, there is no loop gain, 0. 1 minus 0 is 1 only. So 1 times 1 times this x2, then what is the other forward gain? The other forward gain is this one. So it will be -1 times x2 again, okay, divided by the loop, the determinant basically, which is 1 only, because 1 minus 0, as there is no loop gain, as there are no loops. So I am explaining it, but still you should understand it by yourself, because in SFG this is just a cakewalk for you, right? We did it multiple times, questions like this. Okay, so this should be cakewalk. So still I explained, but I am not wasting much time here. So this, right, it will cancel out, so it will not depend on x2. Now, right, we have u1. So u1 is directly coming over here. Is there any other forward path? No, this is against the flow. Okay, then I have only one forward path, that is 1 times 1 into u1. Okay, now right, do I have any other, like for u2, do I have any forward path? So I can go from here, but again I'm going against the flow. So only this is the forward path, right? So but this is only connecting x2 dot, but I am not able to reach x1 dot. So it is 0 times u2. So what is the final expression? It is x1 plus 0 times x2, okay, plus u1 plus 0 times u2. Okay, so this is my final expression basically. Okay, now what is my x2 dot basically? So x2 dot, right, x2 dot, let's say what state variables are coming in. So is x1 coming, so I can go from x1 here, but again this is against the flow, this arrow is opposite, and again this is also against the flow, so this arrow is also opposite, right? So no, x1 doesn't have any like forward path to x2 dot. So this will be 0 times x1, right? 0 times x1. So now, does x2 have? Yes, obviously x2 have a forward path directly from here. Does it have any other forward path? No, this is against the flow, and again this is, okay, this is with the flow, but this is against the flow, right? I'm reaching the same place anyway. So yeah, only one forward path. This is -1. So this will be -1 times x2. Why am I solving this slowly? To like explain to all of you, right? I hope you solved it very fast, okay, because this is easy for you, cakewalk, because we have done SFG multiple times. So now, right, now we will go to this what do you say, u1. Does u1 have any forward path to this x2 dot? So I can go from here, but now I can go in this direction because this is against the flow. Again I can go from here, again this is against the flow. No, again this is also against the flow. No, u1 doesn't have any path to x2 dot. So this will be 0 times u1. Now u2, yes, it has, obviously, directly from here, right, one gain, and we reach directly to x2 dot. Okay, does it have any other path? No, this has directly only one path. So this will be plus u2. Okay, so this is my x2 dot. Now, right, let's write the y1. So what is y1 equals to? So y1, right, I can directly reach to x1. Okay, from x1 I can directly reach to y1. Okay, does x2 also reach to y1? I can go from here, but no, this is against the flow, and this is also against the flow, right? Against the flow. So no, x2 can't reach y1, but x1 can, and y1 equals to x1 itself. Okay, plus 0 x2. Now y2, can y2 reach? y2 reach basically y2 reach I mean, can y2 be reached from x1? So x1 is here, okay, I can go from here. No, this is against the flow and this is also against the flow. y2 is here, I can't reach to y2. Okay, so x1 will be 0 only, like the coefficient of x1 will be 0 only, plus this y2, right? So from x2 we'll go to y2 directly 1 times 1. Okay, so it is 1 only, coefficient of is 1 only. So yeah, this is basically my state space equations and state space representation. Now let's write the matrix, okay, and the whole equation, right? So x dot equals to, now what will be the order of my matrix basically, right? How many integrators I had 2, right? So order will be 2 cross 2, okay, of a order will be 2 cross 2, but how many state order will be there? So it will be, I mean, n cross 1, so it will be 2 cross 1, state vector order will be 2 cross 1. Okay, now what is the order of the B matrix, right? The input matrix, what will be the order? It is basically n cross m, right? Now what is m here? So I should write here, like in this area itself, n is equal to 2, basically order of the circuit. Now what is m? M is equal to m is equal to 2, because I have 2 inputs, right? So it is number of inputs. Okay, why am I writing this multiple times? To keep this in your head, right? These things you have to remember, right? Just to get an idea how the matrix will look like. Number of inputs, and now p is also 2, right, which is number of outputs. So my A matrix will be 2 cross 2. My B matrix will be simply n cross m, which is 2 cross 2, and my C matrix will be p cross n, right? So it is also 2 cross 2. So everything will be a square matrix. Okay, so yeah, that is done. So A will be 2 cross 2, and A we have got here from here. So it is -1 0 and 0 -1, right? So -1 0 and 0 -1. Okay, and what is this? Like this is x only, plus the B matrix, right? What is the B matrix? B matrix is this one, right? Like 1 0 0 1. Okay, so it is 2 cross 2, as you can see. 1 0 0 1. Okay, 1 0 0 1. And this is the Y matrix basically. So what is the Y matrix? So Y matrix, right? Y matrix is what do you say? Y matrix is 2 cross 2 again. So this is 1 0 again 0 1, just like the B matrix. So 1 0 0 1. Okay, and this is equals to like times multiplied by the state vector. So it is x, right? X. So yeah, this is my Y matrix. Now I have to find the like first I have to write the state space representation. Okay, also I had to find the like transfer function matrix. They haven't told us, so okay, I should write the question, rewrite the question. State space representation, also find the transfer function. Now by transfer function they mean the transfer function matrix. Okay, so as it will have 4 transfer functions. Why? Because this output, right, y1 will have like 2 transfer functions. Due to this u1 ones and due to this u2 ones, we will apply superposition. Okay, now this y2 will have also 2 transfer functions due to this input u1 and this input u2, 2 transfer functions, right? So that's why it is like for 2 cross 2 transfer function. So what is the transfer function basically? So again, right, I will tell you what is the transfer function equation. It is Si minus A inverse, right? Now you will like scold me because, sir, why are you telling this? We know that this is C is over here and B is over here. We don't forget. Okay, easy to remember. So yeah, this is C times Si minus A inverse. So like this is simple only because this is identity matrix and this is also identity matrix. So C and this B, right, are identity matrix, so multiplying them will be very easy, like we don't have to do anything. Okay, so this is, let's color them. Okay, so right now C is I only. Okay, and this is I only. Now what is Si minus A inverse? So Si minus A inverse basically, so what is Si is this one only, and minus A inverse, so this is S plus 1 0. Okay, 0 S plus 1 inverse, right? And this II is just 1, so I can ignore this I. So this becomes like the divided by the determinant, which is S plus 1 whole square, and this is just, this will get swapped. Okay, and okay, this is diagonal matrix, so it will be simply 1 by S plus 1, and so I hope you remember that this will, like after finalizing, this will be, this is, if this is lambda 1 lambda 2, okay, repeated diagonal matrix, so this will be 1 by lambda 1 1 by lambda 2 if we do the inverse for a diagonal matrix, right? So for a diagonal matrix, if I have lambda 1 lambda 2, okay, 0 0, then if I do the inverse, it will become 1 by lambda 1 1 by lambda 2, okay, and 0 0 to remain diagonal matrix, and the eigenvalues will just inverse. Okay, simply. So yeah, that is another short trick. So this is S plus 1 0 0 1 by S plus 1. Okay, so yeah, this is my transform function matrix basically. So this is my T of S. Okay, so now, right, T of S matrix basically 2 cross 2. Okay, so now is there any other method? Okay, this was the method 1. Okay, using state space diagram. Okay, state space. Okay, wait, let me bring this to the bottom. Okay, is there any other method? So any other method, right, what we can do is simply use the principle of superposition. So I will find the output for one of the input, turn off the other input, then I will find the output again for other input and turn off the like first input, right? So method 2, superposition, right? Superposition. So what I will do is simply copy, not this one, okay, this one, because that was for state space in time domain. So I will solve this in Laplace domain now directly. Okay, so yeah, like we will use the SFG formula, like the Mason-Gain formula, but we will solve this individually, right? So I will make this smaller. Okay, now I will solve this. So one is, first one I will solve the first one, which is, let's say, y1 over u1, and I will make u2 equals to 0. Okay, so when u2 equals to 0, y1 over u1, what is the transfer function, like which element will this represent in the transfer function matrix? Okay, guess. It will represent the t11, right? T11s. Why? Because like I will explain later. Okay, I will explain later. This will represent t11s. Now u1 is here and y1 is here, so how many forward paths do I have? I can go from here. Can I go from any other place? This is opposing the forward path. This is also opposing. No, this is also opposing. So I can only go in this line. So this will be 1 by s. Okay, forward path gain is 1 by s only. Now what is the associated loop gain? So this is one loop. Okay, this is another loop, right? We have two loops. Is there any other loop? This is what I am saying. I can go from here. No, but this is opposing the flow. So no, this isn't a loop, right? So I have two loops, and this is already, like, I'm going through this loop, right? So this will be not present in the numerator. This will be only present. What will be this? This will be 1 minus, basically, what is the loop gain? Minus 1 by s. So it will become plus 1 by s, right? So I'm not writing the delta right now. Delta will leave out. Okay, so this is the trick, right? You don't solve delta right now. Delta you solve at the end. Okay. Okay, now you go for y1 upon u2, right? Y1 upon u2 when u1 is 0. Okay, now if u1 is 0, what do I get? What transfer function element does this represent? This represents the y12. You just write like this one. Okay, the actual meaning of this I will tell you, but to remember, right, the first term, like first number will come over here and the second number will come over here. What does this mean? This means the first row, second column, first row, second column. Okay, so like that you can understand, but conceptually what does this mean I will tell you after like expanding the equation, right? So t12 of s, what is this? So I have to go from u2 to y1. So u2 is here and y1 is here, right? So I can go from here, 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 here. Yes, I have a forward path. Is there any other forward path? I can go from here. Okay, I can go from here also. Okay, that is very interesting. I can go from here, like from here. Okay, now what is happening is I'm going through two loops, so my associated loop gain will be 1, basically 1 minus 0, it will be 1. Okay, so this is what is the gain of this forward path, 1 by s square. And if I go from here to here, what is the gain of this forward path? It is 1, like 1 by s, 1 times minus 1, 1 times 1 by s. Again, this is minus 1 by s square. So this is 1 by s square minus 1 by s square. So it becomes 0, right? It becomes 0. So it becomes 0. So basically, right, t1 to s, and yeah, so this becomes the numerator becomes 0 itself, because the forward gain, like plus 1 by square and minus 1 by square, upon delta it will be 0 only, right? t12 will be 0. Okay, that we got in the previous method also, right? So now y2 upon u1 when u2 equals to 0, when u2 equals to 0, right? So when u2 equals to 0, what does this element represent? This represents the t21s, right? t21s. So if this represents t21s, what does this mean? Basically, right, so I have to go from u1 to y2, right? So u1 to y2, is there any forward path? From here, no, this is opposing the flow. From here, no, this is also opposing the flow. From here, I'm going out of place, right? I won't be able to reach to y2. So yeah, this is 0 again, so I don't have any forward path again. So this is 0 by delta, so this is 0 only. Now the last one, I have to find y2 upon u2 when u1 is 0. So when u1 is 0, this is t2 to s. Okay, so t2 to s, basically, right, I have to go from u2 to y2. So I can see one forward path. Is there any other? No, this is against the flow and this is going some other direction, right? So I have only one forward path, and loop gain is also there. This is a isolated loop, right? So this will be minus 1 by s, 1 minus 1 by s, which is a 1 plus 1 by s, and this is 1 by s only. So this is 1 by s and 1 plus 1 by s by delta. Okay, by delta. So yeah, this is basically my transfer function matrix. So now, right, what I can do is find delta. What is delta? Delta is basically 1 minus 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 1 by s. Okay, let me write here 1 minus of minus 1 by s minus of 1 by s plus basically minus 1 by s times minus 1 by s. This is each loop gain, right? Each of the loop gains are minus 1 by s, right? That's why. And these two are isolated. I mean, these two are non-touching. These two are non-touching. Okay, then I have to multiply these two also. But I have to stop here because this is the number of loops. After that, after this 3 non-touching loops, it's not possible because I only have 2 loops, right? So yeah, this will be 1 plus 2 by s plus 1 by s square. Okay, so my delta is this one, right? Delta is this one. So what I will do, I will multiply s square both on numerator and denominator. Okay, I will see a pole zero cancellation basically. So let's see. So my t11, right, t11 of s, if I multiply s square both on numerator and denominator, what do I get? I get like this one. So this will become s plus 1 and this will become s square plus 2s plus 1. Okay, s square plus 2s plus 1. So this will be s plus 1 into s plus 1 whole square basically. So this is the formula, you know, s square plus 2s plus 1, this formula you know. So this is 1 by s plus 1, right? So this is 1 by s plus 1. So as we got in the basically first method, right? So t22 will also be similar. Okay, it will be similar again. So this is similar only, right? So this and these are similar only, so this will be same only. Okay, so I can write here directly that my t22s will also be s plus 1. Okay, so yeah, again I can write the whole matrix. So whole matrix is same only, so I will not rewrite, I will just copy and paste. Okay, this will be my whole matrix. So what I was mentioning, right, that t11 and t22, all those significance. So this is my, let's say, y1 and y2. Okay, and this is my basically t11 of s t. I think I have done this already, but to refresh your mind, t21 of s, t22 of s, and this is u1 and u2. Okay, now let's say this, all these are in Laplace domain. Okay, for now all these are in Laplace domain. Okay, okay, so all these are in Laplace domain. So now if I like rewrite this, right, if I rewrite this, what will this become? So my y1 of s and y2 of s becomes, like, I'm doing matrix multiplication here. This is t11 times u1 and t12 times u2. So this becomes t11 of s times u1 of s plus t12 t1 of s times u2 of s. Okay, now this is t21 of s times u2 of s, not u2, basically u1 of s plus t22 of s into u2 of s. Okay, yeah, so this is my transformation matrix. So along this row, right, this is basically equal to my y1s. So what I can see is y1 of s equals to, I will copy this again, so here what I can see, if I make u2 0, I will get the ratio of y1 upon u1 equals to t11, right? So what does t11 represent? That u2 0, okay, y1 upon u1. So that is exactly what I have written here, right? This one, right? Or not this one, right? u2 is 0 and it is the ratio of y1 upon u1. Okay, like that you can derive the other transformations also. Okay, so yeah, from here that is the actual formula, right? That significant form, like that from here we can understand. Okay, so what does that mean conceptually? For remembering purpose, okay, you can simply remember this is 1 upon 2, so this will be 1 2. Okay, first row, second column, right? Remembering purpose, you remember like that, but conceptually this is the actual like what is telling, right, what is telling in the like equation. Okay, so yeah, now let's go to another question. So this is the 47th question basically. So we have to check whether the state space diagram is controllable and observable or not. So this is simple only. So what we can do is basically write the state space equation. From there we can check, or like from the state space diagram also we can check. Just remove the this one waste terms. Okay, so I will copy this one. So I'll paste this one. Okay, this seems like a controllable canonical form, so this seems like always controllable, but let's see. So what I will do, I will remove this 1 by s, this 1 by s, right? Remove this 1 by s. Now, right, I will write time domain expressions. This is x2, so this will be x2 dot. This I should have done earlier, but okay, fine. Before removing, I should have done this, but yeah, we're not going with the procedure. So this is x2 dot, this is x1 dot. Okay, now I have to write the state equations basically. So my x1 dot equals to x2 itself. Is u involved? No, u I can't reach, right? This is against the flow and this is no path, so u is not present. Okay, now anything else is present? No, nothing else is present, right? Nothing else is present. Now my x2 dot u is present, right? U is present. So I will write this like in time domain. So I will write this u of t and y of t here. So this will be u of t u of t and y of t. So x2 dot equals to x2 dot equals to basically u of t is coming here, okay, and like we have no loops, right? We have no loops, that's why I'm writing simply like this. If we had loops here, so I have to use Mason's green again for individual like inputs, okay, for u of t, then for x2 of t, then for x1 of t, as I was solving during the start of this chapter, right? Like that, okay. So yeah, u of t is coming over here. Now x2 of t is also coming to the x2 dot, so this is minus x2, okay, minus x2. And is x1 coming? X1, no, x1 can't come, right? This is against the flow, okay, against the flow, so x1 can't come. So we have only like this minus x2 only, right? Minus x2 only. Now actually actually if I were to wrote here like this, x1 is also here, right? So this will be also minus 2 x1, okay. So yeah, this is my state space equation. Now let's write the output equation. So my output equation equals to this one, right? So x1 is directly coming over here, x2 is coming. Is there any forward path? Yes, there is, right? This is another forward path, right? So it is simply like this is 1 times 1 y1, and this is also 1 times 1, right? So it is x1 plus x2, right? Basically forward gain, right? This is 1 gain, okay, 1 times 1, and is also 1 times 1. So I have two paths. So yt equals to x1 plus x2. Now is this controllable? Yes, right, because my x2 is a function of input and this x1 dot is a function of x2, so this system is controllable, okay. Controllable, okay. And is this observable? Yes, this is observable, right? Why? Due to this x1 plus x2, right? Due to this x1 plus x2, as my output is dependent on both, like as my output can see both the state variables, right? Both x1 and x2 it can see. So this is observable, okay. Now right, this is method 1, okay, using state diagram. Now let's do using that Kalman's test, right? So using Kalman's test, so for that I have to write the state space representation first. So this is my x dot matrix, okay, and what is my E matrix? It is basically minus 2 1, okay. So this is like, this is minus 2, this is 1, and this is 0, like there is no x1, and this is minus 1, right? So 0 minus 1, this is x1 x2, right? X1 x2 plus bu, right? What is b? So b basically, right, b is this u, right? So x1 is not related with u input, but x2 is, like directly, okay. So this will be 0 1 basically. X2 is, right? X2 is x2, yeah, x2 is, right? X2 is, this is u, and y equals to basically 1 1, right? So this is 1 1, and this is again x1 x2, right? X1 x2, okay. So now like what you do, you do the Kalman's test method. So what is the method 2? So I'm solving using Kalman's test. So method 2 is Kalman's test, right? So what do? You know A, you know B, so you simply solve that. This is A and this is B, this is C. Okay, this is C. So this is A, this is B, and this is C. Okay, so for what was QC? QC was simply B, AB, then A square B, right? Like, but we are only doing for like second order, so we'll only go until here, right? We'll have each of them are column matrices, right? Each of them are column matrices. So now, right, what is AB? B we know. What is AB? AB is simply this, right? Okay, this is like -2 times 0, then 1 times 1, so this becomes 1 only. I'm writing this directly. Then 0 times 0 minus 1 times 1, so this becomes -1 only. This is AB. So what will be my QC? Controllability matrix. It is simply combination of this row. This is B. B is 0 1 0 1. This is 1 minus 1. Okay, 1 minus 1. Okay, 0 1 and 1 minus 1. Okay, so yeah, so like what is the rank? Rank is 2, right? Rank is 2, or the determinant of QC, you can see, is non-zero, not equals 0. Like I can write here determinant of QC equals to -1. Okay, so from here you can say this is controllable, but we already, from the state equation itself, we already got it, right? Controllable. Okay, state equation itself, we know this is controllable. Okay, that was the easier method. This is the bit lengthy method, right? Now let's find the QB, basically observability. So for observability, right, so I will find the QB transpose, right? Not QB, sorry, QO. Okay, QO transpose. Okay, what is it? It is simply C, then CA, right? It will be only 2 because the order is 2, right? We have to do it twice only. Now because the order is 2, we have to do it twice only. So this is C by CA, right? So now, right, what will this be? So this, right, let's calculate CA first. What is my CA? CA, right? CA is basically 1 cross 1, okay, times this -2, this one. So 1 times -2, okay, plus 1 times 0, so this becomes -2 only. So this is -2, and what is this? This is again 1 times 0 times 1 times 1 and 1 times -1, so this becomes 0, right? Each of them are row matrices this time. Okay, so I hope you are understanding the matrix multiplication. This is 1 cross 2 matrix, and this is 2 cross 2, so my end result will come 1 cross 2 always, which is coming over 1 cross 2. So like that also you can cross verify that your matrix multiplication is correct or not. Sometimes we get confused, right, with matrix multiplication of small numbers. Okay, with large numbers it is fine, but small numbers I get confused. That's why I do it like this, cross verify like this, that this should come out to be 1 cross 2 matrix. Okay, because C times A is what? C is 1 cross 2 and A is 2 cross 2. Okay, this 2 will cancel and I will be remained with 1 cross 2, right? So this will be 1 cross 2 matrix. Okay, so that's how you can understand whether the result is correct or incorrect. Okay, that is the main thing. So this is CA, and C we know C is 1 comma 1, right? C is 1 comma 1. So this will be simply 1 comma 1 minus 2 comma 0. So is this determinant? What is the determinant? This is basically 1 times 0 minus 2 times 1, which is plus 2. So it is non-zero, right? It is non-zero, hence observable. Okay, but we know from earlier also, from the equation itself, we found it out that it is observable anyways, right? So yeah, that is the one thing. Okay, I solved using both methods now, using this method and that method also. Okay, so let's solve the another question. So what is this question telling us? We have to find the value of G for which the state space diagram will be uncontrollable. Okay, so like we have been given the state space diagram and we have to find the value of this g, right? G is up over here, it is getting confused with 1. So we have to find the value of g for which the state space is uncontrollable. So what does uncontrollable mean? So we have to make this state, right, independent of the input. Okay, this input should not influence the state. Okay, that is the main thing we have to keep in mind while solving this question. So first what I will do, I will write the state space representation, and from there I will try to use this g and use this g to help me remove the input. Okay, as a function of the what I mean, remove the u from the equation of x2, whatever you name this, right? So I will name this x2 dot and this will as x1 dot. Okay, let me first copy the state diagram and then let's understand, right? So basic idea we got, right? That is the basic thing that you have to keep in mind. How to make this uncontrollable? I have to make one of the state variables independent of the input, then this state space representation will be uncontrollable. Okay, that is the main aim that I should keep in mind while solving this question. Okay, so you solve it by yourself, then you see my solution. So again, right, I will write the time domain expression to write the state space equations, right? So like time domain, basically I have to remove, first I have to name the state space variables. This will be x1, this one will be x1 dot, this will be x2, this one will be x2 dot, right? So what I will do, I will remove the integrators basically. So to remove these ones. Okay, and this is my x1 and this is my x1 dot. Okay, and this is my x2 and this is my x2 dot. So now I will write the state space equations. Okay, so my x1 dot equals to, simply these two are coming right from here. So it is like u is coming twice. Is there any other loops here? Let me check if there are any other loops. So I can go from here. No, this is against the flow, this is also against the flow. Okay, no loops for this one. I can, no, this is also against the flow, this is also against the flow. So I am relieved there aren't any loops. Okay, so this u, right, u is coming from here also and coming from here also, right? So this I can make uncontrollable because u is always available to this state variable. Now but to this state variable what I can see is u is coming from here, but it is coming from here also. So I have to focus on this state variable, right? So I will focus on this one. Okay, so I will not write x1 dot, I will write x2 dot first. Okay, so what is my x2 dot? X2 dot is equals to, simply this is one of the forward path, so u times 1, as there is no loops, so associated loop gain will be 1 only, right? So this is u plus this is another gain block, so this is g times u. Okay, g times u. Now what is this? This is x2 times minus 2, right? x2 times minus 2, so this is minus 2 x2 to make this uncontrollable, right? So what is x2 equals to? It is u1 plus g minus 2 x2. Now to make this uncontrollable, this has to be 0. To make state variable like state independent of input, right? To make independent of input, we have to make make it 0, right? Coefficient of u should equals to 0, right? So that means 1 plus g should be equals to 0, that means g should be equals to minus 1, and this is simply my answer, right? I don't have to do anything else. Like while in the solving the question also, you don't worry about anything else. You have to just make the system uncontrollable. You do that. What will be the lengthier approach? The lengthier approach will be to use Kalman's. Okay, and there what do you do? Okay, this is the method 1. Okay, best approach is one. Method 2 is what? Use Kalman's. How will you use Kalman's? So like here the state diagram is given. in some question the state space representation is given, like ABC matrix are given. So from there you write QC, okay, QC as a function of ABC, right? Like QC you write this is what order, this is second order, right? So QC you write, okay, this B and then AB, right? Now what do you do? For uncontrollability you make QC equals to 0, I mean the determinant QC equals 0 for uncontrollability. Okay, you make QC equals to 0. So yeah, from there you will find a relation for G, okay. Like G will come out to be some number, from there you can find that G, right? So this is method 2. So this is Kalman's method basically. Okay, so yeah, this was I think it for this question. Now let's go to another question. So this is another question. What you have to do is, like, obviously you are pausing the video, right? You pause the video, then solve the question, then you see my solution, right? That is very important. So we have to find the state space representation of the state space diagram. So like this is also easy question only, but we have multiple things here, so just let's be just a bit careful, okay? As we have multiple loops I can see, multiple for paths I can see, then just be a little bit careful and solve slowly, okay? So we have to find the state space representation, which is easy only, right? We have done this multiple times. Like this is the most favorite asked topic of state space. So yeah, so I will copy this one, okay, paste this one over here, okay, then remove the one by terms, okay, and sorry, before removing, right, I always forget, I have to write a state state variables also. So what is this? So I will name this as x1 and this as x1 dot okay, I will name this as x2 actually, and this one as x2 dot, okay. That is the convention generally what I follow. So whatever you want to name you can name, right? Okay, because there are no options. So if there are options now, in like most of the standard questions they will give you the state variables, like they will give you that this one is my x1 and this one is my x2, because without that your answer and their answer may not match. But then again you have to interchange the rows and columns, right? Then your answer will be matched, okay? Just they have interchanged the x1 and x2, that is the difference, okay? So yeah, this is x1 and this is x1 dot, the x1 dot. Now what I will do, I will remove the one by terms. So I will remove the one by terms, okay. Now what I will do now, right? So simply I will write the x2 dot in terms of, okay, let me thicken this pen. I will write my x2 dot in terms of u of s and my other state variables. So like x2 has a forward path through x2 dot. Does this have any loops? So what I can see, no, this is against the path, this is with the path, this is with the path, but again this is against the path, and this is going to the output itself. And so this doesn't have also any loop, okay. So yeah, we don't have any loop, so we can solve this peacefully, okay. So now here, right, x1, so can x1 reach x2 dot? So x1 I can go from here, but no, this is against the path, right? So my x1, right, my x1 can't reach x2 dot, so only it will be a function of x2. So x2 is from here going to here, so this is minus L1 times x2, minus L1 times x2, and I'm reaching x2 dot. Now input, yeah, input it can, oh sorry, so let me first name the input and output as time domain expressions. So this is c of t. I hope you are not confused anymore that this is not unit step, this is just the input, right? And this is c of t, okay, don't get confused, right? Okay, this is so this is basically a times x2 dot, like u of t into a, right? So plus a times u of t, okay. So yeah, this is what you can do. Now what is my x1 dot? Basically x1 dot is basically this one, right? So x1 times minus L2, okay, we can reach. Can x2 reach? Yes, x2 can also reach, right? x2 is g1 times basically g1 times x2 basically. So x1 is minus L2 times minus L2 times x1. So I mean x1 dot equals to, so minus L2 times x1 plus g1 times x2, right? So this is also coming over here, right? G1 times x2. So yeah, this is what we get. Now let me do this for like the input is coming. Is there any input path? So I can go from here to here. Yes, there is an input path, right? There is an input path. So don't forget the input also. So input is again a times 1, a times 1. So I am getting the x1 dot. So this is plus a times x1 dot, no, plus a times ut, right? Plus a times ut. So am I forgetting anything here? So this x2, right? I can come from here. Is there any other path? I think I can come from here also, right? I can come from here also. So that's the trick, right? That's the trick. Okay, so yeah, just be a little careful with all this. So there is some hidden trick in this. So I can come from here also. So when there are too many paths, right, too many things going on, just slow down a bit and solve very carefully and check for other paths. So x2, right, can come from this path also. So what is the gain of this one? This is minus L1 times 1, and we reach here. So this will be minus L1 times x2, right? So yeah, these are the two things basically. Now what is the output? Now is my output directly available from the input? Yes, it is, right? Because I can go from here and from here. Okay, so this is also available. So c of t equals to basically this a times 1. So this is a times u of t plus what else is there? So this, right? So we have basically is x2 going to the output? Yes, this is 1, like g1 times 1, again 1. So it is going to the output. So x2 times g1 basically, and this x1, right? It's obviously we can see this is going to the output, right? Is there any other path? I can go like this one also, right? I can go like this one also, right? So yeah, this is also again another interesting thing. I can go like this one also. Okay, so my x2, right? x2 times minus L1 into 1, right? So this is minus L1, right? Now plus basically whatever this x1 is times g2. So this is simple only. X1 doesn't have any path. No, x1 also has a path, right? X1 can go from here also. Okay, x1 also has another path. So x1 into minus L2 and x1 into simple g2 everyone can see. Okay, so yeah, just be careful about all those things. Okay, just be careful. It's like if you miss one thing, then it will be very difficult. So yeah, so now I will write the state space representation basically. So my state space representation, right, it will be equals to so this x2 dot doesn't have any disk because this is at this side, right? So this side there aren't any paths. Okay, so only x2 can reach and this u can reach. So I will write the x1 first. This is like minus L2. Okay, and x1 can only reach from here. Okay, it can't reach from anywhere else. So this is minus L2. So minus L2, and this is g1. Okay, and this is minus L1. So g1 minus L1, g1 minus L1 basically. And what is this? This is okay, what is this? This is minus there is no x1 term here, so this will be 0. Okay, this is x2 actually. So this is basically this is x2, so this will be minus L1, and yeah, okay, sorry I zoomed in a bit. This will be minus L1, and I have x state vector right here. So now what will be this, like what will be my input relation? B matrix. So this one is A also, this one is also A, so this one will be A comma A, right? A comma A times C of t. And what is my Y? My Y is simply will be a row matrix, and it is like it is dependent on the state variables also, which is like minus L2 G2. So G2 minus L2 so this becomes G2 minus L2, and this is what, this is G1 minus L1, so this is G1 minus L1 times X plus, now right, this time, this is a very rare occasion, my D matrix isn't 0, right? D matrix isn't 0. So what is my D matrix? So D matrix is simply A times U, so it will be A times U. So what is the order of the D matrix? I hope you remember, right? It was, what was the order? It was P times M, right? So P is 1, CISO system, single input, single output. So P is 1, M is 1, so it will be only single element, right? So we only get single element. So yeah, this is a bit lengthy question actually, but that's fine. Okay, but like the careful thing, what you have to careful about, this other path, right? Okay, this other part you have to be careful about. That's why like sometimes SFG becomes very difficult, as you can't see. Okay, so draw it very carefully in your rough pad or whatever you solve, right? Draw it very carefully, the SFG. Okay, you might not see the path. Okay, so it is very important, else your question will be wrong again. Okay, so yeah, that is basically important. So now let's go for the next question. So in this question, find the state, we have to, okay, this is again something, find the state space diagram, okay, of the block diagram, basically of the block diagram given below. Whatever, find the state space representation of the block diagram given below. Okay, so this is the block diagram. Okay, now take a pause and convert this into the state space diagram, and from there we can do the state space representation. Okay, so what is the state space representation basically? So I have already written it down to not waste time. So I hope your like whatever you drawn, right, matches with this one. Okay, so I have chosen this one as x1 and x1 dot, and this one as x2 and x2 dot. So here, right, I can see I have multiple paths. Okay, multiple paths. So each added is a node. Okay, each added is I made it node, and each point I made this as node. Okay, make as many nodes as possible, no issues, right? So yeah, if you convert this one, you get something like this. Okay, now I have to find the state space representation. So for that, what I will do, I will remove the, again, this 1 by s terms, right? So like this is, we have done multiple times, so still I've already defined the state variables. Okay, so I will just remove the 1 by s terms. Okay, I hope you are solving, right? You have to solve this first, then you see my solution, then it will be truthful, right? So 1 by s terms I will remove, then simply write the state equations. Do I have any loops form? So if I come from here, no, this is against the flow, this is also against the flow. So this is, if I go from here, this is against the flow. If I go from here, this is against the flow. No, there is no loop in this. But is there any loop here? No. Is there any loop here? No, all of these are against the flow. So I am again like relieved, right? So but still be careful. Okay, so first I will write x1 dot. What is x1 dot? So x1 dot, right, x1 dot I can come from u, 5 times u. Okay, that is one thing. So I will write 5u. First I should write this sequentially, so I will write in terms of x1. So x1 will come minus 1 x1 here. Is there any other path? So if I can go from here, can I go from here? No, I can't, right? So it is only minus 1 x1. So minus 1 x1. Now x2, right? What about x2? So x2 can go from here. Can it go from anywhere else? It can't, right? This is against, this is against. So it is minus 2 times x2. So minus 2 times x2. Okay, now what is u, like in terms of u? So u is 5 times 1, I mean 5 times 1, so 5u, right? Any other possible way? No, this is against the path, this is against the path. So this is 5u, right? This is 5u. Now what is my x2 dot? Okay, my x2 dot is basically due to x1, it is coming from here. Is there any other path? No, right? So due to x1 I can come here from like only from this place. So this is minus 3x1. And due to x2, is there any other path? Due to x2, this one only. Is there any other? No, this is against, this is also against, right? This is minus 4x2. So minus 4x2, right? So I get this path, and due to input, do I have any other path? So 1 times 1, yes, only one path. I can't come from here, right? So it is plus u. Now what about the output? Output, I'm coming from here, is there any other path? No, this is also against, and this is also against the path flow, right? Flow. So only y. So input, can input reach? No, this is against the path again, and this is also against the flow. So input can't reach the output, right? But my y of t equals to x1 plus x2. Okay, so like x1 plus x2. Okay, so yeah, now let's write the like state space representation. So I've solved this basically. So depends on what you choose as x1, x2, you have to change the rows and columns, okay, of the matrix, else everything else will be same only. Okay, so you have to basically make the transpose. Okay, so this will be simply minus 1 minus 2 minus 3 minus 4 x1 x2 plus this input. What input is? This one is 5, okay, this one is 1, and this one is u. And what is my output? Output is simply 1 comma 1, and this is x1 x2. Okay, yeah, I think we have to end this lecture now, because like this lecture has already been gone like 1 hour. So summary will be done in the next lecture. I'm really sorry for that. Okay, so yeah, as this lecture will be extended to 2 hours, so yeah, we'll do the summary in the next lecture. Okay, thank you for watching.